like to start by thanking Patty for putting me right before lunch. So better than after lunch, yeah. Okay, well, I'm happy to be here today, and I hope what I'm going to talk about is instructive and helpful. You may end up thinking or asking yourself, how does this relate to safety? What it is we're looking at technologies to count motorcycles. So how that relates to safety, or one way is, have you ever ridden up to a traffic signal, and at the stop line you're the first vehicle in the queue, and the signal doesn't change, okay? So we need better ways to detect you guys. So that's part of this, but most of it is on free flow type facilities. Is there a question?
No, talk to Austin, City Austin, they detect bicycle right.
Okay. Yeah, the point is we can detect bicycles even, but you got to have the right technology.
Which one is yours?
That one.
Right here. Sorry about that.
So yeah, you can detect pretty small vehicles, but you have to have the right technology and have it in the right place too, and know where you're going to be detected versus anywhere in the lane. So I'd like to start with a graphic that shows, we've talked about some of this before, and I'm going to go through this fairly quickly. The bars above the line indicate that there was an increase from the year before of motorcycle crashes in the pretty pink color there. And these are national statistics, by the way, but the same thing held true in Texas. There were increases over about a 10-year period leading up to this study, and you know, the counts that we were seeing in the vehicle miles traveled of motorcycles were not parallel with the number of crashes and fatalities. So, you know, it didn't take anybody real smart to say, okay, we're probably not counting them very well, so that's the reason for the study. And these are crash statistics. 1997, motorcycles were 5% of the fatals versus 2009, they were 14%. So those are pretty staggering statistics. Motorcycle crashes are 37 times more likely to result in a fatality compared to auto crashes. So we're all aware of this, but just to reiterate that just very quickly, what we're talking about here in motorcycle exposure is how much are motorcyclists exposed to traffic, and how well are we determining that through some metric that we use. The typical measures that we work with are, again, vehicle miles traveled. So the way we get to that metric is we count motorcycles, and then we do an estimate of how many miles were traveled based on the count. So it's an estimate at best, but if we don't count it well, then we're certainly not going to come up with a good VMT, or vehicle miles traveled. So not to belabor it, but I'll talk more about how we measure counts, and then the rest of it is kind of a black box kind of a thing, but anyway. So there are some challenges with motorcycles, as with bicycles, as mentioned earlier. First of all, their size. They're smaller, they don't occupy much space in a lane. So we've got to be in the right place or cover the full lane width. And that's something we haven't really done very well in past years. Some motorcycles have less metal. Some of the technologies rely on a metallic object passing through its field of detection. The patterns of riding, sometimes we have side by side. Not supposed to, but we do occasionally. And if they pass, and even if they're front to back spaced, some technologies don't do very well there either, because it sees one, then it sees another one immediately, and it's trying to process the first one. So we don't do very well when there's not very much metal, it's a small size, and it's passing by at pretty high speeds in many cases. Subcompact cars are a factor because some of the smart cars or smaller vehicles, like some of the Fiats and Mini Coopers and the Smart for Two, are about the same length as a Harley or a big motorcycle. So it's hard to distinguish between those two, so we want accurate counts and trends. Then we've got to be able to distinguish between the smart cars or small cars and motorcycles. Occlusion, what does that mean? It means that a bigger vehicle can hide a smaller vehicle like a motorcycle from as it passes through a detection zone. So a big truck or even a car or an SUV will block the view of a motorcycle. The other thing that we didn't do prior to 2008 was we didn't require states to report motorcycle counts, and that was from the Fed level. Nowadays we have to report a count, so we're trying to get better at the count technology and the methodology of doing that. So anyway, came up with the research project. Here are the objectives, basically to investigate promising technologies and some other things as well, but I'm going to move on. I'm going to leave the second part for later. So the issues, again, there are some factors that we have to work with. Among these, you can probably figure out what most of them mean. Lane discipline means that if we can't predict in a lane boundary, you know, from left to right where a motorcycle or any vehicle is going to be, we might not count it very well. So that's what lane discipline means. I've been told that in California, motorcycles can ride on the lane lines. If there's a traffic that's, you know, congested traffic, if a motorcycle rider wants to ride between rows of traffic, they can do that. So how do we count that? We probably don't. So it's things like that that make the project challenging and interesting. So the other thing is the definition of a motorcycle. I'm going to go through those factors fairly quickly, but the definitions vary as well. We have more, I think we have more Can-Ams and other three-wheelers nowadays, so it's a little bit difficult for some technologies to count those compared to other motorcycles. So there's different definitions. The federal government has one. States have sort of their own. Sometimes it's by brake horsepower, sometimes it's by other things. Of course, the size is a factor too. The lane discipline, if motorcyclists, basically if they ride in the wheel paths, in other words, where a car or SUV would be, their wheels would happen in the lane. Basically, they're about 6 feet wide, lane's about 12 feet wide, so you'd have about 3 feet on either side. So if a motorcyclist rides in those wheel paths, we know how to detect them nowadays. We're not there yet, but we know how to do it. Shoulder detection. Have you ever ridden on a paved shoulder? I should have mentioned that I used to ride back in, let's say a few years ago, on-road and off-road. Sometimes the off-road was not intentional. On a curve, I would take it too fast, in other words. So shoulder detection on paved shoulder, how do we detect there? We have to have a detection zone set up and expect it to happen. Normally, we wouldn't detect that. The vehicle size, I've talked about this. The smart car there, it's somewhat to scale compared against the motorcycle. So you can see it's about the same length. There's some numbers there that indicate what the lengths are if you went out and measured it. But some technologies measure based on what we call a magnetic length instead of the physical length of the vehicle. Inductive loops are one, magnetometers are another. So we can distinguish between a motorcycle and a smart car or other small car more by magnetic length than we can otherwise. Unfortunately, not every technology uses that technology, or uses that methodology, I should say. Occlusion, these are some pictures that show from a camera view that's mounted over the roadway looking downward. What would the view look like? You can imagine that a small vehicle in that traffic stream and one that was even more congested would basically get lost. It would never get seen. So if you can't see it from the camera, it certainly won't count it. So we came to the technology selection. It was based on a number of factors. You can read the list as well as I can. Of course, cost is always a factor. How well does it count? If it's off the roadway, we like it better than if it's in the pavement, simply because we don't have to interfere with traffic to maintain it or install it and things like that. These are the technologies that we selected. The first one, the inductive loops, are the ones that you'll see most of the time at a traffic signal. So if as you approach the signal, if you can see the saw cut, it'll look rectangular. If you ride your motorcycle over the longitudinal saw cut, that's the most sensitive part of it, part of the loop area. You'll be the most likely to be detected, but there's still no guarantee. On a roadway what we're testing is an inductive loop plus an axle sensor. It's called a piezoelectric sensor. Those have been used in the US for probably 20 years. It's a fairly robust technology, but not foolproof. So anyway, that's one we're testing. Magnetometers, as the name suggests, we're looking at the Earth's magnetic field. It's a passive device. It's only monitoring what the field flux lines look like. And as a vehicle passes through that has ferrous metal, it'll change the lines, and that's detectable. So that's the way motorcycles or anything else gets detected. There's a new device on the market. It's a multi-technology system, not very good yet, but it's promising. Video imaging, I showed the picture just the earlier slide, actually has a camera. It's watching the movement of vehicles through a detection zone. The user draws the zones on the, looks like he's drawing them on the pavement, but it's a virtual zone basically. And as the vehicle passes through, it changes the image enough, changes the pixels enough that it gets detected, usually. The last one is actually, I'll tell you in a few minutes, the results of the test. The last one is an infrared device. It's an active versus passive. When I talked about the magnetometer, it's a passive device. The infrared is active. In other words, it's generating energy, sends it out, and monitors how it gets interrupted. So I'll talk about that more in just a second. That was, the acronym was known as the TIRTL, T-I-R-T-L. So we come up with funny names for some of these. Here's a picture in the lower right of what an inductive loop and piezoelectric sensor setup looks like. This is as it's being installed. And Roy knows all about this because he puts them in all the time. But a lot of times you'll see these just as loops, but this one that we're testing is a full lane width piezoelectric sensor. And that sensor again is for the axle. So as you ride across this, we hope the loop detects, but the axle sensor detects the axles or the wheels, the weight. So we hope that both elements of the system detect the motorcycle. If they don't, it's probably not going to classify it correctly, but anyway, this gives you some information about it. The loops are usually 6 foot by 6 foot. Again, if you ride in the wheel paths, they're more likely to detect you. If the piezo is the full lane width, if you're riding in the left wheel path, and it's a 6 foot piezo, you're not going to get detected, which is what we've done for a long time. Not just Texas, but a lot of states have done that. Okay, magnetometers, they're very small. I should have brought one. They're, you can hold it in your hand. It's very light. It's wireless, communicates with the roadside through a wireless RF communication system. The little node costs about $500, but you need about 2 in each station, 2 to 3 per station, positioned a known distance apart to be able to classify vehicles by length. And our tests indicate that they will actually detect motorcycles if they're where you ride across, but it can't be very far away. So within about 2 feet of this sensor node, it's going to miss a motorcycle. Everybody always asks about these, how long is the battery life, because it's inside the node. It's about 10 years, but it's a function of how much traffic, how often it reports. Temperature is a factor, but not a huge factor on these. But we did some tests at one of our test facilities, and some of them lasted even longer. The multi-technology system is designed specifically for motorcycles. It mounts off the roadway. This is a pole at our test facility in College Station. The device there on the near side of the pole in this view is the Migma Systems Inc. detector, and it uses an infrared camera, a stereo visible light camera, and an acoustic sensor. And then it merges all those data as it comes in to try to detect a motorcycle. One thing we found out about that detector is if a motorcycle engine is cold, it uses infrared. So what does infrared look like? Heat differences or heat signatures from the engine in this case. If the engine is not very hot, it doesn't give enough signature to this detector to be able to detect it very well. So just a little tidbit there. But it does have two more technologies. If they detect it, hopefully it'll be accurate. Again, the video system uses a camera and a processor. This picture shows basically a card rack in a cabinet where the processing of the information occurs. So you drew the detection zone, it processes that information in the cabinet, and in most cases, camera systems are binary. It's either yes or no. Was it a detection or not? And it does a little bit with length as well for most of the current systems. For this research, we used a system that's a tracking unit that's even better than most of what were called tripwire units, which only looked at a point or a zone. This one actually did pretty well with motorcycles. It was in the 90+% accuracy in good weather and good environmental conditions. So it's better than video was in the old days, but it's still not as good as some. Still sort of a function of shadows, light angles, changing light, dusk and dawn. Those are very difficult times still for video systems. The final system is what's called a TIRTL. I mentioned it earlier. It's an infrared system. The way it works is it's got two parallel beams that go across the roadway and the two crisscrossing beams in an X pattern. And so it measures both when the parallel beams are broken, so that it can measure a length or wheelbase. So it knows where every axle on a vehicle is. And it also knows a width because it's measuring in the crisscross beams how far the vehicle is from the detector or from the TIRTL unit. It's got a sending unit on, let's call it side A or near side, and it's got a receiving unit on the other side. So it measures in milliseconds how those beams are interrupted, and it's fascinating the way it can work, and it can cover 3 or 4 lanes, which I couldn't believe, but it works really well. I'll just mention the test locations. The one there on the upper left is this bike rally. It was called Biketoberfest. If any of you have ever been to Daytona Beach in October, I was fortunate enough to go and collect the data. Somebody's got to do it, right? So we collected data there on the TIRTL. It's the only one that was left. We didn't have good data, so I'd go down there and enjoy the beach. And the center one is actually a Texas rally in a very small community down south of College Station, at least, west of Houston, called New Ulm, Texas. You probably never heard of it. But there was a British motorcycle rally there. It wasn't a very big one. But anyway, we went down, collected data. It's a very small 2-lane roadway where the motorcycles came in and out. So we did some testing there. Then the third one, the lower right, is our test facility in College Station on State Highway 6. It's a 4-lane roadway, divided, depressed median. And so we've got a 40-foot pole, a mast arm, do a lot of testing there for vehicle detection. So I'll give you some results real quickly. The motorcycle accuracy is on the far left column. If you look down the left, the very far left is the list of the technologies that I've talked about. Most of these did pretty well. except for the multi-technology system. And I should mention that we excluded those where the engines were not hot enough to be detected by the infrared sensor. So we tried to be fair to everybody, but this one, our results say, needs more work, basically. And they're in a second phase currently of improving that one. So what our view is, these need to be in the 90+% range to tell a state DOT or anybody, this is worth investing your money in. The one at the bottom, the TIRTL, was absolutely the best of all. Now, we didn't test it in inclement weather. We didn't. I'd like to do that, but we didn't have the opportunity. I've read some of the findings from, it's actually a unit that's built in Australia. Some of the data from over there that in the rain suggested it works okay. But, you know, I can't vouch for that unless I test it. So I'd really like to test that maybe at Daytona Beach or somewhere nice like that. It does rain there. So for non-motorcycles, that's also important. We don't have to have two devices beside a roadway to count total traffic. So you can look in the second column to the right. Most of them are in the 95 to 98% range. Costs are important as well. The TIRTL is the most expensive, but it's a portable device, or can be. So you can set up on a tripod on either side of the roadway. It takes about 30 minutes to max 1 hour to set it up, and then move it to somewhere else. So it's versatile, it's portable, accurate. So I'm going to end with that. So that's my contact information if anybody has questions, but I'll take questions now. Okay. Okay.
You said that the video detection systems in good weather were 90+%. Was it the inclement weather that brought it down to the 75% for motorcycle detection?
It was that for some, well, let me say, basically the motorcycle detection, because they're small vehicles, is the problem with that. Oops, it didn't go back. Is it showing over there? Okay, so for video, I should have said the fourth one down, the traffic vision is the video. I'm sorry I didn't mention that. The traffic vision is the video detector. It's a tracking unit. The 75% was, we used several days of data collection to come up with the number. Unfortunately, it was not as good some days as others. It did as well as in the 90s some days, so I didn't want to say it was always going to be 90. So I think it's a fairly new unit as well, so I think as they progress and as they make modifications, it'll probably be consistently in the 90s. So does that answer?
It's also the most expensive.
That was pretty expensive as well, and so, as with anything else, you weigh the cost against how accurate it is it portable, and the other things. Is it easy to set up by the user? Most people that are unfamiliar with these technologies are going to have, I said 30 minutes to an hour to set it up. They're going to spend probably much longer than that the first time around. So, other questions? Yeah.
Yeah, the loop piezo combination has about 45% accuracy. I understand that that's probably most of the mass constellations. Does that mean that the current estimates of motorcycle BNT is about off by a factor of 2?
Yeah, thanks for the question. Our results are, I should have said this earlier, but our results are atypical of loops and piezos. And by the way, this system was put in less than a year ago. So, in fact, almost exactly a year ago. So they should be working perfectly, but they aren't. So we've got to still troubleshoot the problem, and to be fair to loop piezo systems that are fairly new, if they're properly installed and maintained, you can get in I'd say the upper 90s consistently. The state of Virginia has done some things with theirs that optimizes how well it works. They've got a way to determine if the piezo starts to fail. because that's the component that usually fails first and unpredictably. So the loops are, I'll say, typically last a long, long time, although they don't necessarily in poor pavements, but they're probably, I'm going to use a number, say 10-year life for loops. Piezos might be, they're usually judged in terms of actual hits, but say 1 million hits or something like that. So calculate the length of time based on some ADT or something, come up with a length of life. So yeah, that's a good point, because that 45% is not a good number typically. So they'll typically do much better than that. Sure.